Hello, I think MPR has joined. Uh, let's wait. I mean, we are 3 minutes early actually. So, what I'll do in the meantime is I'll just start sharing my screen. And hmm, so so this is our course, and we are in the fifth week discussion. Myself. Yeah, so let's see uh, who all are there. We'll wait for a couple of minutes if anyone else is joining. If not, then we'll start. So, yeah. Hello. MPR, can you hear my voice? Can you just confirm whether I am audible or not?
Sir, yes, sir. Audible, sir. Clear.
Okay, okay. So I think you can see my screen as well, right?
Okay. Yes, sir. Yes, sir.
Okay, okay. So yeah, we'll wait for 2 minutes. At 6:05, we'll start. Thank you for joining, and let's see if anyone else joins. That is fine. If not, we'll start the discussion. But let's wait for a couple of minutes. And uh, if you have any doubts, you can interrupt me, and we can discuss there only. So. Uh, or any technical disruption is there. For example, if you are not able to see my screen or not able to hear me properly, please let me know because this video is being recorded and it will be uploaded on YouTube later. So if any issue is there with video or the content, you can interrupt me and let me know. Fine.
Screen is very clear, sir. Voice is also good, sir.
Okay. Okay then. So I think we should start now. It's already 6:05 because if we wait for others, then it will take a lot of time to complete as well. So that's not a good thing for anyone. So anyway, so yeah, I mean, uh, M- MPR, what is your name or what should I call you? Or
Sir, my name is M. Penchala Reddy, sir.
uh, so can I call you Reddy? You were there earlier, right? One class or no?
Okay, sir. No problem.
Okay. Okay then. So what I do generally is for let's say 10-15 minutes we'll revise whatever the content was there in the last week's videos and maybe give some helpful tips about you know some competitive exams or type of things that you should remember for competitive exams. You can mute yourself whenever you have doubt. You can raise the hand or you can directly ask. Fine. Okay.
Okay.
So yeah. So now the first thing is in the last like let's say I would call it as a brief revision of I should not say last, I should just say week 5, uh, based on which your assignment number 5 is uploaded on the portal, NPTEL SWAYAM portal. So what I understood, I saw the lectures briefly. So what I understood is professor has taught you about Reynolds transport theorem. We call it as RTT also, short form. So essentially, this RTT is a it acts as a connection or a mathematical tool. That would be a better way. Mathematical tool to connect uh, system properties to control volume. I mean, I'm writing, this is not a proper definition of RTT, okay? So please don't use this definition in your subjective exams. You'll not get good marks. This is essentially a one sentence summary of a theorem. Theorem is a very well elaborated, very well put in uh, thing, and you can find it in any standard book. But what essentially you should understand is, till this point, you have studied control. No, sorry. You have studied control mass systems, in which there is no mass and energy interaction, and the identity of mass also remains the same. And now you'll be going to study control volume systems. So, but essentially, it doesn't matter what type of system you are studying, the governing equations that should hold true for anything or any physical phenomena. So this RTT gives you the flexibility to modify the governing equations, which you have studied for control mass system, and you can do some modifications and use it for control volume system. So control mass system we have discussed in detail. What is control mass system is essentially, here you fix in control mass system your mass of the system, or mass interaction is not there. There can be energy interaction, but mass and the identity of mass remains same. But here in control volume system, uh, essentially you fix the volume of the system, uh, and it allows you to have mass interactions as well as energy interactions, but your attention is on the volume, the control volume that you have defined. And that is a basic difference between control volume and control mass system. It is evident from the name as well. So this is the main thing that you are studying for this course, for this week or upcoming weeks also. And essentially, RTT gives you a flexibility to connect these two types of system, or at least governing equations and properties that you can study for both. So essentially, that is what a brief understanding of RTT is here. You can refer to any standard book for a formal definition, but this is what it is essentially. And this RTT, can be used to relate mass conservation, energy conservation, and it is not in this course syllabus, but it is also a tool which you can use to study this three governing equations. So the form of the equation will change, but essentially the meaning of the governing equation is it governs the physical phenomena that are taking place there. In this course, mass and energy conservation equations are in the scope of this course. Momentum equation, momentum conservation equation, and RTT, how to apply it, that maybe you'll learn in your fluid mechanics course. Maybe I think it will be on NPTEL itself. So anyway, that is not the point here. So we'll briefly revise uh, those governing equations. I think Narendra is also here, so that is good. So anyway, uh, so essentially, you can write RTT in the mathematical form as dN by dt of the system equal to dN by dt of the control volume plus some this thing plus some this surface area integral. So essentially, you can write this time derivative control volume over rho and dV plus over cross sectional area you can write rho n V relative, this is a vector, and this dA is a elemental area vector. So essentially in class you might have seen this type of representation for this area vector. So essentially it's the same thing. You take a dot product between the velocity relative to the control volume, and it's a dot product between area normal to the area or the unit vector perpendicular to your control surface. So it can be represented as unit vector eta into dA, or you can just write dA as a vector. So essentially you should understand it's a dot product between velocity and the area normal vector. And here n is an extensive property. Small n is capital N by m. So you know this is a representation for intensive property. Since it's mass independent now, you divided it by mass. So and this is the volume, the elemental volume, which we have defined in a control volume, and we integrate over it. So symbol is not V. I just put a slightly different symbol so that you should not get confused between velocity and the volume. So that is the whole point. And remember, this is a volume integral and this is a surface integral. Generally, when we write in this form, sometimes people forget these are not a linear integration. So essentially, you should write it in this format. So it's a triple integral over volume, and this is a surface integral, so double integral. So anyway, for simplicity, we just write control volume and control surface. But you should remember these are not line integrals. These are surface and volume integrals. So based on this, you'll see first mass conservation. So here you put the capital N extensive property as n. So your small n becomes 1. And if you do this manipulation that has been done for you in class, it essentially reduces to the you can write it in this form also, dm by dt of control volume plus m dot e minus m dot I. I am also following the same nomenclature which is followed in your class videos. I is for exit, E is for exit, and I is for inlet. So this is this system should, I mean, it would look like something like this. This will be your control volume. 1 second. So let's say it's a pipe flow. So this dotted area will be your control volume, and some mass is entering and some mass is leaving. So like from system point of view, this LHS of this equation, which is dN by dt of the system, it should go to 0 because mass remains conserved. So that LHS is 0 on right hand side. When you put small n equal to 1, the first term, which is volume integral over the control volume, essentially reduces to rho d volume, and if you integrate, it's the mass of the control volume essentially. So this is your mass conservation equation, important equation to remember. And if you have multiple inlets and multiple outlets, you can take integration over this exit and inlet areas. One assumption that is incorporated in this equation, writing this equation, is this mass flow rate, or you can write mass flow rate here. Mass flow rate is uniform over the respective cross-sectional area. What I mean by this is let's take the inlet of the system. if this is the inlet where your m dot I is coming, you know that on the boundary there will be zero velocity because of no slip boundary condition, and the velocity will be maximum at the center. So velocity profile should look like this, something like this. Exact equations will depend which type of flow regime you are in, laminar or turbulent. But essentially your central axial velocity will be more, and it will be zero at the boundaries because of no slip condition. So at each point across this surface, your mass flow rate is changing. But what we do is we do the area integral over this surface, or I mean, in this view, you are seeing it as a line, but it's actually a surface. So you take the surface integral. Essentially, I can give you the expression. It is like, let's say this is the area A. So you do the integral over the area, and what you do is, if there is a small elemental area dA, and whatever is the mass flow rate flowing through that area, and you do the integral over whole surface, whole area, and divided by total area. So that is what I mean by uh, uniform property. So uniform mass flow rate in this case. So this assumption is valid throughout this discussion. We take velocity, datum height, and all those values as uniform values. Values averaged over the cross sectional area. So then only you can write this term. Otherwise, you'll have to do the surface integral there. And then the second part was energy conservation. So here you put n as a total energy of your system. So small n becomes E by m, which is specific energy. So this contains your internal energy, kinetic energy, plus potential energy, plus since this is a flowing system, I mean mass is flowing in and out of the control volume, you'll have a flow energy as well. This was also discussed in the class, which is essentially PV or P by rho you take at that particular cross-sectional area. So you represent internal energy by U, kinetic and potential energy. Generally we neglect. So we generally take it. We should not write it as zero, but I can write it as generally neglected. Not always. So remember this part, because some of the examples that we'll be seeing, this kinetic energy itself is our objective to find, like the velocity that the exit or inlet. So you don't neglect them everywhere, but many a times you neglect. So, and then this flow energy is there. So please remember that whenever you'll have a control volume system, some mass flow will be coming into the system, some will be going out, and therefore you'll have flow work or flow energy. So its physical interpretation was given by professor in the class, and that is much. I mean, I can't say any more than that, because that has covered everything. I can't find anything which was not discussed there. So you can revisit the class and see. And one more thing I forgot to mention: when you do this area integral, at the outlet, your area and the velocity vectors will be, they'll be having uh, same direction. So their dot product will be a positive value because it's a cos theta, right? So cos 0 is 1. But when you're in at your inlet, your area normal points in exactly opposite direction to the your normal velocity. So there it becomes negative, the dot product, and that's why here mass flow rate at the exit is positive and inlet is negative. And this is true for energy equation also. So in energy equation, you can write it in this form: dN by dt and all the volume integrals, surface integrals. But essentially, after you do the manipulation, by doing some modifications, In the end, you'll end up with this expression, which is useful for solving problems. So this is your difference of heat interaction and work interaction of the system, which is, again, you can write it as d by dt of system. I mean, this term is equivalent to that. And then there will be d by dt of control volume plus you'll have I mean, when you put this small e and then you divide it into u plus PV, that becomes enthalpy. Enthalpy is, H is equal to u plus PV. So this, if you do those manipulations, essentially you will end up with the this form of equation, H plus V square by 2 plus GZ. One second, I'll remove this because it may confuse some people. And again, this V relative dot dA. This is a dot product. So this is enthalpy, which is U plus PV. This is that flow work that we encounter in this kind of system. And yeah, you see, this is a velocity. I mean, here, since we are not dealing with the, moving control volumes, for much of the discussion uh, we'll be talking about stationary control volumes. They are, I think, called as non-inertial frame of reference, but that is not the part of this course. So in that case, you can, for this course or for this class, you can just take this V and V relative as same, and you can move on. So that was the whole point of saying all those things. So these were, you know, conservation equations that you can sort of get by doing RTT. And then an important class of applications in which you do this assumption of steady state, steady flow, energy equation. So essentially this is like, if you see the first part, steady state, that means your properties like H, PV, U, they are not function of time. So that essentially boils down to d by dt of control volume equal to 0 in the energy equation. And steady flow means your mass flow rates are independent of time. So then this dm by dt of control volume becomes 0. I mean, this is a typical this was the explanation given in your class lectures as well, and I think it's I mean, it's a quite uh, intuitive type of explanation. These are subtle things that you should know, because in some of the textbooks, very standard textbooks as well, they just write it as a SFEE, which is steady flow energy equation. So they just drop the term steady state, but it is assumed that you have taken these two conditions and then you can just write it as a short form, SFEE. But ideally it should be SSSFEE. So it's a quite big thing, but this is the correct technical definition of it. And if you do that, then essentially your mass conservation equation will boil down to m dot I summation I'm taking, assuming there are multiple channels of inlet and outlets. It can be one or many. And if you do this and this, so essentially you'll end up with this q dot minus w. And like, since you're assuming this thing, what's it, the properties are uniform over the cross-sectional areas, control surfaces. So in that case, you can just write the surface integral term. dA by dt of control volume will go to 0, and the next surface integral term, you can just write it as m dot E in bracket HE plus VE square by 2 plus GZE minus m dot I HI VI square by 2 plus GZ I. So this is the form of equation it boils down to. Some people, take this negative term on this side and this work term on this side, so that all the signs are positive and you will not get confused. But this is also fine. If anyone can remember this way, that is also fine. I find this way easier because this is just your first law of thermodynamics for your control mass system. You just write it as difference. This is essentially your change of internal energy for that system, and here you just write exit minus inlet. Whatever the properties are there, you just do exit minus inlet. So anyway, whatever the way you like it, you can define it as it is. And one more caution, this was also told in the class, but generally Q dot and W dot are given in kilowatts, but VE, or let's say any velocity, or this Z, datum height, these are in meter per second or meter. I mean, these are in SI units, they are in meter per second or meter. So when you do this calculation, just make sure your units are you are satisfying you are satisfying the units on the both sides. So that was one thing. And similarly, this H enthalpy is also given in kilowatts. So this quantity is in kilowatt, this quantity is kilowatt, but these two are in generally, if you do the calculation, they'll come into watts. So you should be careful there, because if you do the mistake, it's a mistake in which you miss a factor of 1,000. So your answer will be definitely wrong. You'll not be near anywhere. So please remember this, because this is important in solving numericals, which we'll do now. So that is one. And one last thing is about the throttling. This is throttling definition you might have already seen somewhere, but it's essentially a flow through.
Hello, sir.
Narendra.
Sorry to disturb, sir.
Good.
Sir, here H is the specific enthalpy, small
Yeah,
h.
yeah. All small
Therefore,
letters are.
I think unit should be the kilojoule per kg.
I mean, yeah, that is right.
I
So
think,
here, yeah, it will come like this.
Hmm.
Uh,
Kilojoule per kg.
huh.
Yeah. After multiplying, it will be the kilowatt. After multiplying by the mass flow rate, then it
Mhm.
is a kilowatt.
Yeah. So
Yes.
yeah, that is correct.
Yes.
But yeah, that is what you said is correct, that it was wrongly written in kilowatts.
Yeah. Sir.
But the point you should get is, please make sure your units are matching, because
Yeah.
now maybe since you are doing this assignment, you will be very aware of this. But when you finally appear for GATE or any other competitive exam, most of the time in that exam pressure and all the things that you are remembering in your head, you'll forget this small thing, and very simple problem which you could have done it in a minute or less than minute, you'll make a mistake, and that is what silly mistake is in GATE exam. If you have given GATE exam, or if you are planning to do the GATE exam, please remember, in GATE exam, if you have prepared honestly, you'll know how to solve everything. You'll most probably you'll do some silly mistakes, and that's why your rank will be very it will be not good. So that happens because of such small mistakes, which we call silly mistake. So now maybe you'll remember, because we are discussing it multiple times. But finally, just wherever you are taking notes, make sure of writing this when you write this SFE equation. And yeah, so essentially we'll start with problems, but before that, throttling is essentially a flow through a restricted passage, and in many books it is written as isenthalpic process. I mean, it can be, I mean, it depends how you define isenthalpic process. So by isenthalpic, if you mean uh, it's a constant enthalpy process, which is its definition, book definition. So it is not an isenthalpic process. So if you find this expression somewhere, uh, it is not true. What is true is enthalpy at inlet and enthalpy at exit of your control volume will be same. In between, it can be anything. It can increase, decrease, whatever it is. So this type of question, many a times in competitive exam you'll see, and many a times the isenthalpic process answer is also correct. But you have to use your common sense there. If out of 4 options, if other 3 are clearly wrong and isenthalpic process is given, you have to tick that, even though you know that it's not an isenthalpic process, but you can't do anything there. But in case of any interview or anything, especially in research institutes, if by some chance they are asking a question on throttling, never say it's an isenthalpic process. Just say that inlet and outlet enthalpy is constant of the control volume. That's it. So this is also again an important point. And now I think we have covered everything. So we'll start with the problem, but before that, I'll just give you one template. So essentially, your problems will be of 5 types. I mean, first problems are like component wise uh, SF. I mean, I can write. Essentially, it's all component wise. So there you'll encounter something called as a nozzle. Then you'll encounter something called as diffuser. Then there is turbine. Then there is compressor. So these type of problems you'll see from this area. So nozzle, I mean, this question was also asked to someone in BARC interview. What is nozzle? So you should understand essentially nozzle is a device in which you want to increase the kinetic energy of the working fluid, and it is essentially when the velocity or the kinetic energy increases, your pressure or the pressure energy or the static head or whatever it is called, it will decrease. But essentially, if it is a nozzle, and I'm talking about not those supercritical nozzles in which Mach number is above than 1, those things are not part of this course. I'm talking general, like small general application nozzles. There you should remember the kinetic energy always increases. So if you solve a problem dealing with nozzles and your answer gives you velocity at the exit lesser than the velocity at inlet, you have done some mistake and you should go back and check. And in case of diffuser, the kinetic energy will decrease because it diffuses. So essentially, you'll have some working fluid like steam or something which is at very high velocities. You cannot dump that directly into the atmosphere because it will be risky. If any worker or any animal comes into the direct contact with that, it will get hurt. So you use diffusers to reduce the kinetic energy, which results in increase in the pressure. So that is the work of diffuser basically. Turbine, it's a work producing device. So essentially, wherever you have turbine, your W dot, it should come as, if you remember the sign convention of our thermodynamics course, if the work done is by the system or the control volume, it should be positive. So if you solve any problem and if you get work done as negative in case of turbine, you have done some mistake somewhere, some sign convention or something. But your answer should be positive work done here. You can't say anything about Q dot because it can be positive, it can be negative, but W dot should be positive. In case of compressor, it's a work consuming device. So essentially you do work on the working fluid, which can be air or any other gas, and you compress it. So you provide the work. So in this type of questions, your work done should be negative. So if we are getting positive work done for such problems by some chance, that is wrong. So you should recheck everything. And then there is a second category of problem in which these components will be together. I mean, there is one more component, you can call it as a heat exchanger. But in heat exchanger, you can't say directly like some quantity will increase, some will decrease. I mean, this is a heat exchanger, so hot fluid will become colder and cold fluid will become hotter. That is the whole purpose of heat exchanger. So there you can't say anything for sure, but yeah, that is also an important component that will be seen in this type of problems. So if you know these 5 components, and then in some questions there will be combination of 2 of them or 3 of them. So you can apply this control volume to each component, get the required properties, then move on to the next. So how, like, in the direction in which your working fluid is flowing, you should also start flowing in that direction while solving the problem. So that is the whole concept. And now we'll go to some numericals just to get the hang of it. Let's say, see, these questions will be similar to your assignments, okay? Because I mean, this type of questions will be similar only. You can change the numerical values that is in your hand, but the basic concept remains same. So we'll take one problem of nozzle, let's say. So I am giving you an example in which steam is flowing through the nozzle and mass flow rate is given as 0.1 kg per second. Temperature at inlet is 400 degrees Celsius, and inlet kinetic energy is negligible. So we'll just write it as 0. But you understand it's not 0, right? I mean, this is not exactly 0. This is approximately 0. So we are basically neglecting kinetic energy in comparison to the internal energy or the thermal energy, you can say, with the steam at the inlet. And at exit, temperature at exit is 350 degrees Celsius. Pressure at the exit is 500 kPa. And one more thing is given, that the flow is adiabatic. So if you don't know what adiabatic means, it's essentially there is no heat flux or no heat interaction. So essentially Q dot is equal to 0. So, and this is all which is given, and you need to find velocity at the exit of the nozzle, and the second quantity that you should find is nozzle exit area, or AE. So these 2 quantities you need to find. So essentially when you draw a nozzle, this is also important. You know that the velocity is increasing. So essentially you draw it like this. One second. And you show inlet here. This will be your inlet and this will be your exit. And since it's adiabatic, you show it by this type of lines. These are some standard conventions that are followed. First of all, you need to define your control volume. So I'll use some different color so that it is well, you can see it well. So this is, what is it? So this is your control volume. So if you yeah, obviously this is a steady state, steady flow type of problem. These all problems are like that only, so no need to mention it again and again. But if you are solving it, like in some other context, then you should write from steady state, steady flow energy equation, we can write m dot I equal to m dot E, and that is given as 0.1 kg per second. And then you can write again the energy equation as m dot I hi plus vi by 2 vi square by 2 gzi equal to w dot plus m dot E in the bracket he ve square by 2 plus gze. So this bracket is in multiplication here. So now what all is given? I'll use another color to just so that it doesn't becomes too much cluttery. So this is given as 0 because it's an adiabatic flow, and we are neglecting potential energy because the height difference is not that much between inlet and exit. There is no work done by the control volume, so this also goes. And in question it is given that at inlet the kinetic energy is negligible, so this term also goes to 0. So essentially, and these m dot I and m dot E are same. So essentially, if you do those calculation or the simplifications, in the end you'll end up in this equation, which is V2 square equal to 2 H1 minus H2. And if you do the I can write it here itself. It will be whole power 1 by 2. So I'm not doing all the steps of this question, but you should understand it's a fairly simple problem, fairly simple calculation. And now the question is from where you get H1 and H2. So for H1, you have initial temperature, and for H2, actually at inlet, I missed one thing. Inlet pressure is also given, because if not, then you can't find H from steam tables. So for this pressure and temperature, if you search steam table, you'll realize that it comes in the superheated region, and at the exit where this temperature and pressure is given, that part also comes in the superheated region. So if you do refer to the steam table and find H1 and H2 values, I'll just, for your reference, if anyone of you solve this, I'll give you H1 value. You should get 3263.88 kilojoule per kg from steam table, and H2 value you should get 3167.65 kilojoule per kg. And then you can do the calculation, and I leave this to your interest. What is the velocity at the exit? The value, you find out that. And one more thing, are you able to see my screen, or is it frozen or something?
Yes, sir. It is visible.
And you are seeing everything, right? I wrote H1 and H2 here. You saw that, right?
Yes, sir.
Okay. Maybe I'm actually joining from my mobile also, but there it is not updating. So anyway, I think my internet is slow. Yeah, it is updated now. Anyway, and the second part of the question will be the nozzle exit area. So I hope all of you know the formula for mass flow rate, which will be rho AV, or if you write in terms of specific volume, it will be AV by specific volume. So now you know mass flow rate at the exit, you know velocity at the exit, which you just calculated. I mean, one second, I think I should just follow same notation everywhere. This will be VE, HI minus HE, HI, HE, and this will be VE again. So this is essentially what you calculated from here. And a specific volume at the exit, again go to the steam table, and since you know the pressure and temperature, and it's a superheated steam, so you'll get the directly V specific volume from the steam table, and if you do the calculations, you should get area at the exit as some value. I'm not giving you the answers because I mean I can, but these are fairly straightforward, and if you do some work, that's a practice for you also. Then second part of the question, let's say we took a nozzle, right? So we'll take one. We'll take one diffuser as well. So in this problem, it is given that it is a diffuser device. And yeah, before moving on, like this is a nozzle. First problem was nozzle, and there the inlet kinetic energy we neglected. But even if there was some initial inlet velocity was given, you should make sure that your exit velocity is higher than the inlet velocity. Then only your calculation is correct. Otherwise, there is something wrong. And similarly, by the same logic, in your diffuser, your exit velocity should be lower than the inlet velocity. So in this question, you are using air as a working fluid. The Ti or the inlet temperature is 300 Kelvin. Inlet pressure is 100 kPa. So you can straightforward see here 100 kPa is 1 bar, but the temperature is, oh, it's a Kelvin. Then it's fine. Then it's okay. I thought it's degree Celsius, so I was going to say it's anyway. So let it be. And the velocity at the inlet is 200 meter per second. These are the given things at the inlet. Inlet cross-sectional area is 100 mm square, and at exit cross-sectional area is 860 mm square. Here only you can see at inlet cross-section is smaller, at the exit it's larger. So obviously your velocity will reduce and pressure will increase at the exit, and that is the whole point. Velocity at exit is 20 meters per second. Here you can't neglect it, even though it's a very small quantity, but still there is a exit velocity. It's not a zero exit velocity or negligible, because I mean it should come out, right? So then you need to find this thing. You need to find pressure at the exit, and one more thing you need to find is, oh, I think here only the pressure is asked, because I think areas are given, so that part of the question is not there. Anyway, so you need to find pressure at the exit. So let me draw the diffuser. One more convention: you draw nozzle like this, in which your cross-sectional area decreases from left to right, and you draw diffuser in the opposite sense. So here your cross-sectional area increases, because you are reducing the speed, increasing the cross-sectional area. So this is your inlet exit, and your control volume array. This is your control volume. And again, using steady state steady flow energy equation, we have m dot I equal to m dot E q dot I plus m dot m dot I in bracket hi plus vi square by 2 plus gzi should be equal to the sorry, I made a mistake. It should not be qi, it's a q dot, just simply m dot E HEVE square by 2 plus GZE. So now again, let's simplify this expression. It is not specifically mentioned whether this diffuser is insulated not. So if not mentioned, you can just assume it as adiabatic. So that is one trick. If it is not mentioned, you can assume whatever you like, but to simplify our calculations, because you don't have any other way to find q dot, right? So it's better to assume adiabatic, and you can just neglect that term. There is no work done by control volume or work done on the control volume, and this potential energy losses, potential energy variations are also negligible. You can't neglect VE, there is some value for it, and your m dot I and m dot E are similar to the nozzle. So if you do that, if you, it will get cancelled from the both sides. It's not zero, it will get cancelled. So if you do this, you should get HE minus HI equal to VI square minus VE square by 2. Now again, here V is not 0. I'll just change the thing. So here Vi was given, VE also given, and so you'll get the value for this, and it should be in this value, you'll get in joules, so divided by 1000. So if you do this way, you'll get it in kilojoule per kg. So that is how it will be. Yeah, so now the question was, what is the pressure at the exit? So now from this HE minus HI, you can't know anything about pressure, because basically you can write it as Cp Te minus Ti. This is equal to He minus Hi. H is nothing but the like Cpt, right? So from here, inlet temperature at the max, what you can get is, if you assume Cp of 1 for air, you'll get exit temperature. Initial inlet temperature is 300, so you'll get the exit temperature, some value in kelvins. So, but the question asked is they don't want temperature, they want pressure. So how will you go about it is, you'll assume ideal gas equation is valid here. This is an assumption because no other information is given, right? How will you correlate temperature and pressure? So if you do that, what you can do is, then you can write PE, specific volume at exit, equal to R of air into TE. Similarly, PI, VI, R, TI. Now again, if you want, you can take the ratio of these two equations, but then you'll have to find out this thing, specific volume ratio. That is again pain. You can do it from property table of air or something, but let's say we have velocities, right? So you know mass flow rate is given as rho AV or AV by specific volume, and mass flow rate is constant. So V at inlet upon specific volume at inlet upon equal to V at exit and specific volume at exit. So if you use these three equations, essentially what you'll end up is, let's say our objective was to find PE. So in this side, if you take the ratio, it will be TE/TI, and this volume ratio will become ulta here. And again, you use this equation and you simplify this. So this term will remain as it is, and VI by VE will become capital VI by, there will be area here. So area by area at exit and velocity, not a specific volume, sorry, velocity at the exit. So you have all these values given in the question. You have PI also, and therefore you'll get PE. These are slightly complicated calculations, so I'll give you the answers. This will be 319.72 Kelvin, and pressure you should get 123.92 kilopascal. So yeah, so you can see in case of diffuser, velocity at the inlet is higher, but at exit it is lower, and pressure increases. At the inlet it is 100 kPa, but at the exit it's 123 kPa, 124 to be exact. So that's how you can cross check your answers. So whether whatever value you got, it's correct or not, you should do this sense check at the end. So it makes sense here. So we'll proceed with the last example here. So we'll take one slightly complicated problem because time is almost over. So should we take okay. I was thinking, should I take simple turbine or compressor problem, or one coupled problem in which two components are there. So anyway, let me see. Okay, so we'll take one problem in which I'll give you the problem statement. So given, this is our last problem today, okay? So max 10 minutes more. So you have a compressor in which there is an inlet here, and compressed air is getting out from here, and this air goes to a cooler, which is again a heat exchanger, and it exits from the cooler. So this is a cooler and this is a compressor. So you may know this is generally a symbol for compressor, and let's say this is one. We'll just make these points for our better understanding. And you know that you give the work input to the compressor, and since it's a work done on the system, it will be negative according to our sign convention. And since it's a cooler, it will take heat from this compressed fluid. It is air. So when you compress the air, its pressure as well as temperature increases. So you need air at higher pressure, you don't need at higher temperature. So essentially you'll use a cooler in which Q dot will be rejected by the system or the control volume here. So that is negative again according to our sign convention. So anyway, what is given is at point 1, which is the inlet, P1 is 100 kPa, T1 is 17 degrees Celsius, and at 2, I mean after the compressor, the pressure, outlet pressure at the compressor end is 1 MPa. So essentially 1000 kPa, so 10 times compression. And also as a result of this compression, the temperature is increased to 600 Kelvin. So now it's a good practice to keep the unit same. We'll keep this also in Kelvin, even though it is given in degree Celsius in the question, which is quite strange. So 273 plus 17, it will be 290 Kelvin initial temperature. It becomes 600 Kelvin. Then it is given that at cooler, pressure remains constant. So P2 is equal to P3, and exit temperature from the cooler or the T3 is 300 Kelvin. So this is given, and to find, what you need to find is what is first part is what is compressor work, but here mass flow rate is not given. You can assume mass flow rate as 1 kg per second. And second part of the question is we need to find how much heat was rejected by cooler. So these two quantities are asked. I have taken this example because it correlates, combination of two components. Instead of compressor, if there is a turbine, so instead of negative work done, it will be a positive work done. Other things remain same. So yeah, so this will cover everything. And nothing is mentioned about the heat transfer. So we'll assume the compressor to be adiabatic. So now to approach this problem is, follow the flow as your working fluid is flowing. So your air is going from 1 to 2, 2 to 3. So you also should go from 1 to 2, 2 to 3. If somewhere you are stuck, then you need to, this approach works 90% of the time. Sometimes you may need some trick in which you'll have to start the problem from last to first point, but generally from first to last it works. So if you do that, let's say first we need to find what is the compressor work. So now you take compressor as control volume, and you know that mass flow rate at the inlet and outlet is same, so no need to write it again. You can directly write the energy equation, which is again here we are representing it by 1 to 2, right? Inlet and outlet. So you can write Q dot, let's say compressor. So we'll use the subscript C, but it is again cooler is also there. So anyway, we'll use C and we'll use something for cooler. So M dot 1 H1. This is inlet, right? I mean, on LHS we take inlet, right? Yeah, because on the RHS it is negative. So V1 square by 2 GZ1, it will be equal to work done for the this thing by the control volume, or the work done of the control volume. It can be positive, negative, whatever it is. So this is your energy equation. You neglect the potential energy changes because it's at the same elevation, inlet and exit. Nothing is meant. The compressor is assumed to be adiabatic, so this term goes to 0. And what about the velocities? So the information about the velocities is also not given, and typically for turbine or compressor, the velocity terms are also very negligible compared to the enthalpy. So these terms are also generally neglected, and here also we are neglecting them. So essentially, your work done of the control volume becomes m dot, because m dot 1 and m dot 2 is same. It's a steady flow process, steady flow. So it will be m dot 1 h1 minus h2. So now your intuition should, like, math says this value should come negative, and you can see here it is coming as product of m dot and h1 minus h2. This is always positive. Mass flow rate cannot be negative. So this term, if it is negative, then you are okay, and it is negative because you are compressing the air. So essentially h2 will be higher than h1. So this term will be negative and your work done will be negative. So that is correct. So this is also one sanity check you can apply while solving such problems. And now m dot 1 is 1. And how do you get h1 and h2? You go to the, uh, you can use this thing, CPT, because this is air. So you have CP of air 1.005 kilojoule per kg Kelvin. You know T1 and T2. So essentially you know everything. And if you put that thing here, so it will be like, wait 1 second, I'll change the color. So if you do those calculations, so so 290 minus 600 Kelvin. So if you do this, this value should be around 317 kilojoule per kg negative. So not kg actually, sorry, we can't multiply with we multiplied with the mass flow rate side, so it will be kilowatt. And the next part was, what is the heat rejected by cooler? So again, go back to your, now for this is for the first part. Now for second part, take cooler as a control volume, and again let me take, I'll write cooler here because see we used there. Here it will be m dot 2 h2. We are neglecting velocity and gravity head, so those terms will be neglected directly. I am not writing them again. Work done in this control volume m dot 3 it will be, and here it will be h3. So this term will also go to 0 because there is no work done by the cooler. So essentially m dot and m dot 3 will be same, 2 and 3, because of steady flow process. So q dot cooler will become m dot, because that is the same mass flow rate that is going everywhere. So it will be h3 minus h2. So again you can write h as m dot cp t3 minus t2. So if you put those values, 1.005, T3 was given in the question, 300 minus 600. So you should get minus 305. Yeah, something like that. So again, this is not kilojoule per kg. Sorry, this is kilowatt. So again, this value is negative, which is what we expected because it is the heat rejected by the control volume. So according to our sign convention, it should be negative, and it came negative. So these are the all questions that similar type of questions you'll face, and I hope after this discussion, you'll be able to solve your assignment problem and next problems that you'll face in your competitive exams. So we'll stop here. It's 10 minutes extra, but we started 5 minutes late, so essentially 5 minutes extra. Anyway, so I think Reddy already left. Narendra is still here. So Narendra, shall we stop?
Sir, may I ask one any doubt regarding this any properties of the air?
Yeah,
Time is already any over.
tell me.
Because in the last any session, Abhik Dev sir has taken a similar any problem, and in that any problem, he used the values of enthalpies from the air table. My question is, the doubt is that when will you use air table or when use this any formula Cp into the delta T?
When you don't have
Sir,
a table,
I have doubt that again. What is my doubt that while referring the air table, because pressure and temperatures are given, but values are given on a temperature base only.
okay.
Are not mentioned there. They are given it a low pressure.
To be honest with you,
Yeah.
if you want exact answer, you should follow table, because
Table.
here the whatever I have solved, the assumption that is not explicitly told is Cp is constant.
Yeah. Yes.
But you can see the temperatures are 600 Kelvin, which is 250 degrees Celsius more
Yeah.
like. So there Cp will be slightly different. It will not be a big difference. I'll tell you.
Yeah.
If you use the air table, or
Yeah.
that property table for air, and if you calculate this Q heat rejected by the cooler, you'll get 307 kilowatt.
Yeah.
But by doing this, you are getting 305 kilowatt. So there is an error of 2 kilowatt in my calculation, and that is because of assumption that Cp is constant.
Yes.
So if your objective is to get exact answer, you should definitely follow a table. But what happens for steam, you have a steam table.
Yes, sir.
But for air, generally the CPT for enthalpy works.
Yeah.
So if you have table, go for it. If you don't, then you can do CPT. For
Yeah.
example,
Yes.
gate exam or anything, you don't have any table, right? So you can do this way, and you can save your time. So
Okay.
essentially it depends. If you want exactly the right answer, go for table. If you want somewhat approximate or quick answer, you should go for CP delta T.
Okay.
So yeah. So I think anything else? This last assignment solutions are all correct, or any doubt is there?
Yeah. Everything is right, sir.
Okay. So I think we should
Actually,
stop.
already I have solved that last assignment. So I submitted. But in the last class, I have not asked this my query to Big Dev sir. Hmm.
No, you should
Because
ask.
sir, why I am that is putting the word in the while referring the steam table, we'll use the pressure as well as the temperature. But in the air table, we are using only the temperatures. Pressures are not any using, because values are given there in the table on the temperature base only. So that's why I have that is any doubt.
Yeah, actually, see
Yeah.
here, your pressure at the inlet of compressor was 100 kPa,
Yeah.
but it became
1000.
1000 kPa, 10 times.
Yeah.
And in cooler, it is at 1000 kPa only. So this value that CP I have used here.
Yeah.
See, we assume air as an ideal gas, but
Ideal gas.
it is not in reality. Okay. So
Okay.
its CP will change with temperature as well as pressure.
Yes.
So whatever I have done here is approximate, you can say,
Under the assumption of ideal gas.
under the assumption of ideal gas, and CP is only function of temperature, and that remains constant.
And for the
So,
ideal gas only.
so it is, I think, ideal gas as well as this calorimetrically perfect gas.
Yeah. Yes.
So this is an approximate way to do it. It's a quicker way.
Yeah.
And
Yeah.
see, when you do exactly, you are getting 307. When
Yeah.
you do this way, you are getting 305.
Yeah.
So even if in gate exam, if you do, they have some margin for putting your answer. Like if you
Yeah.
put 100, they have some plus minus 1%, right?
Yeah. Yeah.
So you will end up at fairly close value only. So that's why I am using this. But
Yeah.
again, everywhere you cannot carry tables. For Steam, you can't do this assumption, right? So there you need to use Steam table, and in question the values will be given. But generally, if you see competitive exams, let's say for railways or civil services, uh, and if you are taking mechanical as a optional, there you'll find only air or water, and
Yeah.
they expect you to take CP1 for air and for water 1.4.2.
Yeah.
So there, and the options are also like that only. They'll not be very close. So there, this will work. Even in gate, this will work.
Okay.
But in subjective exams, you should mention clearly that we are assuming H equal to CPT, and CP is not function of temperature, or it is not changing with temperature for given temperature operating range. So if you write it this way, the examiner will not deduct any marks.
Yeah.
Okay.
Okay, sir. Thank you very much. I have
Okay.
taken more time
No, no, it's
because
fine. It is fine.
I have any more convert with you, sir. I am very free with you.
Yeah, that is
That,
good only. And actually, we don't realize. See, this doubt you had, right? So
yeah.
if anyone else sees my YouTube video or attend my class, I mean this class, so he or she will also have the same doubt, right?
Yeah.
So if you don't answer, you'll not get answer easily.
Yes.
You'll have to look in the internet and all that thing. You will waste your time. So if you have any doubt, you can directly ask. No issues. This is the whole point of this.
Sir,
Uh,
these things will not be clear by internet or even reading books also. I
yeah,
know.
yeah. So better you ask here only. Whatever you doubt you have, you clear here and go home and start practicing.
Yes.
You are preparing for any, like, which year you are in?
Yes, sir. Actually, I am not any student. I am a staff. I am faculty
Okay.
in a engineering college.
Where?
Rajiv Gandhi Engineering College, Chandrapur.
Okay. I went
Is it
to, I
is a
mean,
interest I am any appearing. I joined this any course.
acha, acha. But
Actually, my area is I am actually teaching subject of to first year engineering graphics, and in the
okay.
second year in a theory of machines, in a design
Oh,
side. But in the last 5 from the last 5 years, I am
uh,
teaching this any subject
you're teaching?
thermodynamics at
Uh,
present. Uh,
okay. So you are, like, let's say if you are not appearing for any exam, but your students will appear, right?
yes,
So
students will apply.
yeah, so this is for their benefit, I guess.
Yeah,
Uh,
definitely, sir.
yeah. So, and one more thing, what I was, something came in my mind, but I came to Chandrapur once. Not Chandrapur, Wardha.
Varda, yeah.
My, I mean, my BTech is from NIT Nagpur, na.
Yes,
So
sir.
I had one friend, Sanjay Raut. He was from Wardha.
Okay.
So one time we went. There was, I think, a marriage in his house. So
Yeah,
yeah, so people are very good there. Nature or the weather is not good,
weather is not good.
but
Particular Chandrapur is not good. Nagpur is some anyway. It's an okay, but Chandrapur is an.
but yeah, I like the people. People are nice.
Yeah, that is any main thing, sir.
Yeah.
We
So
can adjust the weather, but we cannot adjust the peoples. The people should be any good.
yeah.
Friends should
So
be any good.
if your students ask such questions or any other type of doubt, you can ask me. We'll discuss. Okay.
Yeah, definitely, definitely, sir.
Okay. Then shall we stop now?
Okay, okay. Thank you very much, sir.
Okay, Narendra. Good night. Have a good
Night.
night, and
Okay.
see you
Good night.
next Tuesday.
Okay.
Okay, chalo. Bye. We'll stop presenting. We'll stop recording as well. Yes.